Good evening, students. Here I am. This is my third lecture, and in this lecture we will be discussing chopper control of DC motors. Previously, we have discussed the control of DC motor, separately excited DC motor by using half wave and full wave rectifier, and here we will see how to control a separately excited DC motor using choppers. And what are choppers? Choppers are basically DC to DC converters, and here also we will see that using different configuration of choppers we will be operating in just a minute. Yes, yeah, we will be operating in all the four segments, right? In DC motor control using converters, we have seen that we have been able to operate in the first quadrant and the second quadrant using full wave rectifier, and using the half wave rectifier in only the first quadrant. Using the chopper, we will see that how can we operate the DC motor in all the four quadrants, right? First quadrant being the forward motoring, the second quadrant being the forward braking, the third quadrant being the reverse motoring, and the fourth quadrant being the reverse braking. Now, first we will come down to type A chopper. There basically we will study about A, B, C, D, E. There's 5 types of choppers, but to start with, we will discuss the type A chopper, which is more popularly known as a step-down chopper. Now, in the step-down chopper, the configuration of the chopper is like this. Again, needless to say that this RLE load basically represents a DC motor load, a DC motor. Now, this is the configuration of the step-down chopper. This is a switch, electronic space switch, right? This is my supply DC voltage. This is my diode used. Now, as you can see that with the step down chopper, only the first quadrant operation is possible. That only the first quadrant operation is possible. That means we can only operate in the forward motoring mode. That is the output voltage will be always be positive, and the current will always be positive. That is, this is my reference direction of the output current, and this is my reference direction of the output voltage, and both this voltage and the current, the reference directions will be followed. That is, they will always be positive. That is, the polarities of this voltage will never be changed, and the direction of the current will always be entering into the load. Now, here we have seen that this is a T on, this is a T off. This T on plus T off together makes the one time period of the switching cycle. And now during T on, that is when this switch is turned on, we can see that the voltage across the motor is Vs. That is a supply voltage. So therefore we can see it's Vs. And when it is turned off, when the switch is turned off, then what happens? This diode is forward biased. And therefore the current continues to freewheel through this diode, and as this diode conducts, the voltage across the output becomes 0. So we can see that during T off interval, the output voltage is 0. This is the plot of the output voltage V0. Similarly, it continues, and the current, as the switch is turned on, this S is turned on, so the current rises up, and this charges this inductor. This is the current rising up and charges this inductor, and as soon as you turn off this switch, what happens? The current starts to decay through this diode and freewheels through this path. So this is the my waveform of my current, right? Supposing this current has this average current I0 average. This is not the instantaneous value of the output current, and from here we will get an average current I0 average. Now, considering the duty cycle. Now, what is this duty cycle? Duty cycle is the ratio of the on period to the one period of switching cycle, T on. That is that is D is equals to T on by T, where T is equals to T on plus T off, right? So from here, from this waveform, we can very easily calculate. So if T on, so from this equation, and replacing T on by dt, we can get T off is equals to 1 minus dt and T on is equals to dt. These are very simple. You will just understand as you go through it. And V0 average, from this waveform you can easily calculate the V0 average as D into the supply voltage. That is just this is as simple as that. V0 average is 1 by the time period, the total area enclosed by the on time period, that is Vs into dt. Time period gets cancelled. What is left is dVs. This is your average voltage. So your I0 average, the average value of the current through the load will be the average voltage minus this back EMF divided by R. So why not L? Because basically the average voltage across the L is 0. That means the L has no role to play as long as you consider a DC supply, right? So for this chopper, the output voltage becomes dVs, that is the duty cycle times the supply voltage. This has already been told that it always operated in the forward motoring mode, as the current and the voltage always remains positive for this type of configuration, type A chopper. So using type A chopper, only forward motoring may be obtained. Now you know this relation for DC motor, that is the speed is given by VA minus IA RA by K phi. For this configuration, we have shown VA to be V0. For this is the motor, then this is the armature, and the voltage across the armature, that is VA, is the V0. So VA minus IA RA by K phi, and here IA is I0. So using these two variables, we can show that N is equals to V0 minus I0 RA by K phi, and N is equals to replacing V0 by dVs by K phi minus I0 RA by K phi, and further replacing I0 by torque relation, torque is equal to K phi IA, we get N is equals to this. This represents a straight line equation, as you have seen in case of the converter also the same thing, and here with different values of the duty cycle, the speed will vary as such, right? Okay. This is 41. So we see that as the values of the duty cycle reduces from D1 to D2 to D3, the no load speed also reduces from N1 to N2 to N3. Now let us describe this type B chopper. Type B chopper is, this is my type B chopper. So what is this type B chopper? Type B chopper refers to the step up chopper. The previous one was a step down, and this is a step up chopper. Now using this type B chopper, we will see how that we will operate in the second quadrant, that is in the forward braking mode. From the plot itself, we can see that in the forward braking mode, the output voltage will always be positive, but the current will reverse its direction. That is, the current will be negative. Now current negative means basically the torque of the motor will reverse. Now this is the configuration, and here I have shown that using type B chopper we can obtain second quadrant or forward braking operation. In this operation, power is fed back from the load to the supply. Means for this operation, the DC power from the load will be fed back to the supply, right, to the supply. So this is more of a kind of regenerative braking, you can say, where we have studied earlier that the power is fed back from the load side to the supply side. Now this is a circuit diagram. This is a configuration of the step up chopper. For the step up chopper, this configuration needs to be remembered and practiced. And here also S is equals to on means the switch turned on, and S is equals to off. Now we see that whenever this switch is turned on, what will happen? See, this EMF will feed the current through this. So my reference current is this, and the current actual flowing is opposite to I0. That means the negative direction of the current. So this as on, so this is reverse biased by Vs. So as this is turned on, this back EMF will force the current through this switch S. So this path is short circuited and the output voltage becomes 0. And as soon as the switch is turned off, what happens? This DAD is forward biased. So this V0 and the Vs becomes the same. So that is why V0 is equals to Vs. So this is the waveform. Just in opposite to the previous case, we see that during T on the voltage is 0 and during T off the voltage is Vs. In the previous case we had seen that during T on the voltage was Vs, but here it is just the opposite. And we see here that and similarly, if we calculate the average value of this voltage, we will see the voltage comes out to be Vs into 1 minus d by t into t, that is 1 minus d into Vs. The average voltage falls to be 1 minus d times of the supply voltage, V0 average. Now what is called a step up chopper? It is called a step up chopper because its utility basically comes to operation, or its utility basically comes to use when the power is fed back from the load side to the supply side. Now we see from this relation we can see that here the load, here this V0 is acting as a supply of voltage, and so V0 average is Vs into 1 minus d, so 1 minus d. So if we calculate this supply voltage, that will be V0 average by 1 divided by 1 minus d. And d will vary from 0 to 1. So with varying values of d, the supply voltage will always be greater than this V0 average. That is why it's called a step up chopper. Okay. So okay. This is the circuit diagram, and this average comes to be, as I've told, Vs into 1 minus d. Now as I0 is negative, because of the second quadrant operation, E is greater than V0 average. That is, just as I've said, this E is, see from the circuit, the current is flowing in this direction, that is opposite to the reference direction of I0. So this E must be greater than V0 average. That is why it is forcing the current against V0. So this E0 must be greater than V0 average, or E must be greater than Vs 1 minus d. Therefore I0 is equals to E minus V0 average by R. That is E minus Vs 1 minus d by R. Or I0 is equals to E minus Vs 1 minus d by R. This is given by equation 2. These are very simple mathematical calculations, and you will get to know as and when you go through this notes. Now from this we can just calculate this E. We can just change the sides, and we calculate this E is equals to Vs 1 minus d plus I0 into R, and we know from the relation that E is equals to K phi n, where n is the rotations per minute speed. So n becomes this. Further, if we replace the current by torque, we get this from the relation. We again and again showing that torque is equals to K phi IC. Again, so see, these are different characteristics for D1, D2. For D1 is less than D2. So this is my n. You see that as you reduce this D1, as you reduce this D, as the D becomes smaller, the no load speed, these points becomes larger. It rises up along the n axis, right? And this. So at this point, the torque is 0, right? So on this side, it is as the torque reverses. So as the torque reverses, then this in further increases above it. Now, why the torque reverses? The torque reverses. See this direction. This sign for the step down chopper was minus, but here it has become plus. Why it has become plus? Because the direction of the current has changed. So this torque also becomes negative owing to the change in the direction of this current. So this is basically the step down chopper. Now, okay, so for now it's step up and the step down chopper, and for the step CDE I'll give you in the next video. Thank you.